Good afternoon, everyone, and welcome to today's AFMS seminar. It's a great pleasure to introduce our speaker, Elisabeth Guazzelli. Elisabeth Guazzelli is an expert in particulate multiphase flows, including fluidized beds, suspensions, and sediment transport. Elisabeth is a CNRS researcher, previously leading research groups at the University of Aix-Marseille, and now at the University Paris Cité. She serves as rector of the International Center for Mechanical Sciences in Italy, and has been an editor for the Journal of Fluid Mechanics since 2005. Elisabeth is a fellow of the both American Physical Society and the European Mechanics Society, and she has received prestigious awards, including the Euromech Fluid Mechanics Prize in 2016, and the APS Fluid Dynamics Prize in 2023. And today, Elisabeth will be talking about the rheology of dense granular suspensions across flow regimes. Thank you, Elisabeth.
Okay, just thank you for inviting me to give this talk. My first visit to Australia, virtual visit, sort of, and thank you for this very nice word, Anand. So I can just, can you see my screen? Everything is fine? Yeah.
Can you make it full screen now? Yes. Yeah.
Is it okay now? Yeah.
Now it's perfect. Yeah.
Okay. So I can start now. And yes, I wanted to talk to you about the rheology of dense granular suspension. And is it okay? The sound? Hello?
You're okay, but I think maybe there's some echo.
There's
sure if
something
one of the
going on?
audience has got the, yes, I think it should be fixed now. Sorry for the interruption.
It's okay? It's
yes,
okay?
that was perfect. Yeah.
Okay, can I start? Yeah, okay. So I wanted to talk about the rheology of dense granular suspension, and this is a work that I've been doing since a while. And this is something that of course, we started in Marseille with Olivier Pouliken, and we continue with Franco Tapia, who has been with us since a while. And of course, we started with very hard suspension, really odd spheres, and I will talk about it. And then we moved to smooth particle with Pascal Osiu, Shang Wei Hong, and also we collaborated with Mie Shirara at the University of Tokyo. So this is really a work which has been going on since a little while. And I just want to talk a little bit what is this complex mobile particulate system that we want to discuss about. And this is something which is very common in engineering and nature. And I just want to give you 3 examples. The first is the flow of concrete, and this is this little image on the left, and you can see this concrete flowing here. And concrete is made of different size of particle with a binding fluid, and actually they can adjust the type of fluid and the type of particle to adjust the flowing. And this is a substance which is really very common in the world. After they said in Wikipedia that it's the most common substance made used by human after water. So, and it's very, to make concrete, it's very energy demanding. So that's, and we want to understand how it's flowing. The second example is the red blood cell, the blood, basically, which is a suspension and that we have in our body. And here it's a picture of red blood cell, and red blood cell has this kind of flexible cell, which are about 9-10 micron, and they are like little plates, and they are flexible because they can squeeze in small capillary. And you can see with it's very concentrated, and there's different type of flow, because you can have very slow flow in small capillary and very fast flow in artery. And the other example I want to show you is this debris flow. And I'm thinking in general about debris flow, avalanche, mudslides, all this landslide, all this type of flow. And this flow, you can see here, it's a picture from this blog about landslide. And it's made in, it's a picture, it's a movie actually, made in Irgraben in Switzerland. And it happened that there's debris flow and they have instrumented this site for a long time and they can capture it. And you can see here the big boulder, which are carried by a sort of mud flow, and actually it's particle with smaller size. And really what, just a few examples, and you see that there's different size, small particle, larger particle, different flow. It can be laminar, it can be inertial, viscous, it can be turbulent, nearly. Well, you can see here for the debris flow. And really what we want is to understand the rheology of suspension across the different flow regime. And so I will tell you a little bit first about the viscous suspension rheology, and then I will move to granular rheology, trying to unify granular and suspension flow. Then I will show that you can also unify the different regime, inertial and viscous. And then I will talk about soft particle, and that we develop a soft granular rheology. And I will talk about first viscous suspension rheology, and this is something very basic. It's the suspension viscosity. And if you have a suspension of neutrally buoyant, non-Brownian, monodisperse art sphere, here it's a little sketch showing that you're going to shear them. They are neutrally buoyant. Just to do that, you just adjust the density of the fluid and that of the particle. And if you look at just dimensional analysis, if you think about a little bit about the physics, there is a viscous scaling of the shear stress. So the shear stress tau is proportional to the shear rate gamma dot. I have defined gamma dot like that, with E being that the elongational tensor. And you can see that it's proportional, and eta F is the viscosity of the suspending fluid, and you have just the viscosity of the suspension, relative viscosity of the suspension, which is just depending on the volume fraction. And this is dimensional analysis, which is telling you about. And here on the right, I have a graph where I collected many experiments and also some numerical simulation showing you the viscosities, this relative viscosity, which is just the shear stress divided by eta F gamma dot. And you can see that it's increasing with volume fraction. And we know that since Einstein, that when you add particle to a fluid, you're going to dissipate more. And the basic idea behind that is because if you have one particle in a shear can be it's just the addition of a rotation and an elongation. So if you add just the particle, the particle will rotate. There is no additional thing like that. But in the rotational field, but in the elongational field, the particle resists to deformation. Therefore, it's dissipating more, and it's creating disturbance. And that's the computation that Einstein did in the beginning of the 20th century. And he found that you have the viscosity of the suspension, which is always larger than the viscosity of the pure fluid. But you can see that the formula of Einstein, which is just that the additional the effect of the first effect of the volume fraction is just 2.5 phi, which is written here. It works when it's extremely dilute. Then you have to if you want to compute the viscosity for a larger concentration, you have to take into account the hydrodynamic interaction. This is what was done by Batchelor and Green in 1970. And you have the further correction in phi square. But you can see that this account for the viscosity only, this is the line which are here. Einstein is the dotted line, and Batchelor and Green is the dash dotted here. And you can see that it works for very small volume fraction. But when you increase further the volume fraction, you have to account for hydrodynamic interaction between the particle, but also direct contact. And because when you hit basically 30–40%, the particle enter in contact, and there is also direct contact between the particle. And you can see that the viscosity increase and then diverge at a volume fraction phi c, which is smaller than the random close packing of 64%, because the particle that we have here, which are sphere, are frictional, and really this volume fraction, this critical volume fraction, will depend on the size distribution, of course, of the particle and the surface interaction. And really, when there is friction, it's smaller than the random close packing, and it's between 54 and 62%. So when you see that, this is the basic suspension viscosity, you see that it looks like it's quasi-Newtonian behavior as a shear stress. But in fact, it's a little bit more complicated than that, because you have normal stress. And in particular, if you think there is this particle pressure, and actually the suspension mixture is incompressible, but not the particle phase, because the particle phase can expand or contract. And actually, because it's a dispersed phase, okay, while the suspension mixture is completely incompressible. And you can define a pressure, or more generally a normal stress of the particle phase. And there is again viscous scaling of this pressure. And this pressure is proportional to absolute value of the shear stress, because it's independent of the sign of the shear rate. And again, you can define a relative normal viscosity, which is only dependent on the volume fraction. And it's really, there have been some idea that it's analogous to the osmotic pressure that you find in colloidal system. And actually, on the right, I have collected, it's much more difficult to measure this particle pressure, and I will discuss later how to measure that. And this normal viscosity is plotted here. There's some volume fraction for different, and so I collected different experiment and also numerical simulation. And you can see that the same divergence with volume fraction as the shear viscosity, and it's diverging at the same phi c that you can see here. And this particle pressure is crucial to really model the two-phase flow. And it's crucial in modeling, for instance, the slip between the different phase and the different system. So I will discuss. So this is basically what we know for the viscous suspension rheology. I gave you a little overview very quick. And now we're going to move to how we can have a different point of view. And this is a granular rheology. And it's an alternative description that we can call pressure imposed rheology. And instead, you can see that there is system like the erosion of sedimented particle and the action of shearing flow, or granular avalanches here when you have immersed granular avalanche, where in both cases, the gravity control the level of stress experienced by the particle phase, whereas the volume fraction is free to adjust. while in the previous slide that I show you, which are the classical view, you have a suspension which is confined between two plates and or rheometer, for instance, and shear. So in this system, the volume fraction adjusts to the flow condition. And this is basically what you have when you have a dry granular system. Because when you have a dry granular system and you have a little sketch here on the left, you shear this granular system and you need to impose a pressure so it can flow. And there is a friction in the latency lows in this granular, for this granular system. And the pressure, there's this pressure on the top of the plate and the shear rate gamma dot, which are imposed. And the shear stress, tau, is proportional to the pressure, like in a classical frictional law, with an effective friction coefficient mu. And there is also the volume fraction. And this volume fraction and mu are function of a single parameter. This is dimensional analysis, which is also telling you that, which is this inertial number. This inertial number is gamma dot d. D is the size of the particle, the diameter, divided by the square root of p, and rho p is the density of the particle. Okay, and you can see that it's another view because you impose the pressure, and you can think about the same thing for a suspension. You can think about the pressure imposed rheometry, where you have a suspension here, and you have a top plate, which is porous, and you can impose pressure while you shear, and you can also have a effective friction coefficient and a volume fraction, which are depending on the dimensionless number, but instead of being this inertial number, it's a viscous number. And previously, I discussed the volume imposed rheometry with actually instead the quantity or the shear viscosity and the normal viscosity. And you have a viscous scaling of the stresses. So this is two different views, and you will see that we show that it's equivalent. And just to give an idea about this dimensionless number, what they come from, I mentioned the inertial dimensionless number for the granular flow, and actually it's more I square that you should think about. It's a ratio between two stress scales, the inertial stress scale, which is just scaling which was given by Backnall in 1950, in this paper of 1954. And it's rho p d square gamma dot square. And it's a ratio between this inertial scale and the external confining pressure. The viscous dimensionless number, it again the ratio between two stress scales, but you have a viscous stress scale, which is eta f gamma dot instead, and it's a Newtonian scaling. Okay. So it depends if you are inertial or viscous. And actually, we built this pressure imposed rheometer, and this is the little sketch on the right here. And it's a rheometer which is with an annular cell. The bottom can rotate, but here the important thing is that here you have a top porous plate where the fluid can flow through, but not the particle. And so you impose from the top pressure, and actually you can measure the volume fraction because you have here a position sensor on the top plate, so you know exactly what is the position of the top plate. You can measure, of course, gamma dot because with the rotation of the bottom plate, and you measure the shear stress with a torque sensor, and the pressure because you impose it. And actually, if you if you rotate, for instance, very slowly, actually the fluid is flowing out, and you can reach really very close to the jamming transition. And if you go very fast on the other, you actually the fluid is going inside, and actually you actually what you do by changing the gamma dot is that you adjust the volume fraction, and your volume fraction is adjusting to the flow. Okay, so with this system, actually you can measure the particle pressure because you can impose it, and you can examine the rheology very close to the jamming transition. And I will give you an example in two cases. In the dry case and the immersed case, we have used, this is in this paper here with Franco Tapia and Olivier Couliquen, we have this polystyrene sphere, which are pretty big, as you can see. They are 580 micron, and we can measure their roughness, their sliding and rolling friction, and we can ever use them in a rheometer in dry condition, or immerse in this PEG, which is a very viscous solution, very viscous fluid. Okay, and in the case where it's inertial, which is on the left here, we plotted the effective friction coefficient and the volume fraction versus this inertial number I, and you can see that you have mu is increasing with I, and phi is decreasing, and this is actually proportional to the square root to I. Actually, you can see, or the square root of I squared. On the right side, this is a viscous suspension, and we plotted mu and phi versus J, which is this viscous number, and you can see that it's mu is increasing with J, and again phi is decreasing with J, but it's going like the square root of J. Okay. And the important thing is you have the same critical value in dry and immersed condition for phi C and for mu C, and which is really depending on the nature of the contact between the particle. But since having the same value in the inertial case and the viscous case tell you that when you are very close to jamming, what matters is really the contact between the particles. And that means that this is what it's showing. Okay. And now I can just normalize everything by this critical value near jamming, and you can see that here, this value, it's much better to normalize things. And another thing what I can do is take this data and plot them in the classical way somehow. So I can, on the right here, for viscous suspension, I can use mu and J and phi, and I can derive the shear viscosity and the normal viscosity like that. The shear viscosity is mu divided by J, and the normal viscosity is 1 over J. And you can see that we recover completely the formulation that we had in the volume imposed condition. Okay, you have viscosity which are diverging with phi. On the left side, I have plotted the inertial case, and we use a Bagnall scaling. You remember that I gave you this Bagnall scaling. So we normalize the shear and stress and the pressure by rho p d square gamma dot square. And actually, you have coefficient, it's not viscosity, which are also plotted versus volume fraction, and you see they increase with volume fraction. And in both cases, they diverge like phi c minus phi with the power -2 in both cases. And I can show you this more clearly by plotting here in this log-log plot here to show you that there is this divergence with the distance to jamming. And this is in agreement, this asymptotic behavior is in agreement with 3D numerical simulation with where you account for frictional interaction between the sphere. Okay, so just to tell you that, to conclude this, tell you that we can have an alternative way of thinking in terms of the rheology, which is this pressure imposed. And pressure imposed and volume imposed are similar. They agree with each other. You can go from one to another. Now, another thing is that you can see that this is working for inertial system, but also for viscous system. Now, the second step we wanted to discuss and we tackled is how we go from the viscous to the inertial system. How can we, now that we have unified granular suspension flow, in the sense that you can describe them in a volume imposed situation or a pressure imposed situation, now we can think about how we can unify the inertial and the viscous region. Okay. And really, the idea is to look at the transition from a Newtonian to a Bagnonian rheology. And the Newtonian rheology is the viscous granular suspension. This is just what I showed you before, just before, with this viscous suspension. And how we go from this viscous suspension to the inertial granular suspension with the Bagnonian rheology. And actually, the transition is described by the Stokes number, which is the ratio between the inertial and the viscous stress scale. And this is Stokes number is rho p d square gamma dot divided by eta f, and it's basically I square divided by j. We don't have so many studies on that. Actually, the first study is a beautiful study by Bagnol, and in this paper, which is in 1954, he really gave the different scaling when you are in, he gave the inertial scaling and the viscous scaling of the stresses. And really he had a beautiful experiment where he had this is a sketch on the left of the apparatus, and he had a quet flow. And the thing which was extremely smart and extremely interesting is that he had membrane here on both sides, and he was able to measure the bumping of the particle on this membrane and to measure the pressure. And he was probably one of the first to really rationalize this idea of the pressure. And he made some experiment in a very inertial regime, but also in a case he had a suspension of sphere which were about 1 millimeter at a very large volume fraction, where he was able to capture the transition, and he didn't plot it with the Stokes number at that time, but basically it's on that range of Stokes number where he observes the transition between 12 and 100. Okay. Of course, there is also some more recent numerical simulation looking at the viscous to inertial transition. And I gave some paper here, from the paper from Truelson, but also this paper of Amarsid. Here it's a plot from the paper of Truelson, where you have discrete element method plus lubrification. It's in 2D, and they use they look at the viscous and inertial rheological regime, and they found that they could be unified as a function of a single dimensionless number, by adding the contribution. So they basically plotted phi and mu versus j plus a coefficient I square, alpha I square. So you will see that we get in the experiment. So we did revisit this transition. So we use the same rheometer as I discussed before. And we used very large PMMA sphere, polymethyl metachloride sphere, which are about 5 millimeter, immersed in a fluid of varying viscosity. We characterize very carefully the property of this particle, the surface roughness, the interparticle sliding friction coefficient. And we run a rheometer in 2 types of rheometry. In volume impose, by having a loop, here it's a sketch again of our rheometer on the right here. You can see that we have the porous plate here, and we have a captor here measuring the height of the top plate, and we can have a loop, a retroactive loop on the position of the top plate, which means that we are in volume imposed rheometry, or we can have a retroactive loop on the pressure here, which is imposed. And so we can run the rheometer either in volume imposed or in pressure imposed rheometry. Okay, so this is rheological data collected in volume imposed rheometry. So this is this PMMA sphere. They are suspended in a various mixture of water and Yukon oil. Yukon oil is just oil which is miscible with water, made by union carbide, and by varying the percentage of Yukon oil, you can vary the viscosity. So you see we have 4 different viscosity, and we have 4 different volume fraction. And here we plotted the viscosity, shear viscosity, and the normal viscosity versus the Stokes number. Okay, so you can see that clearly if the Stokes is smaller than 10, you have a sort of Newtonian regime where the viscosity is a constant. Okay, it's independent of Stokes. Then you have a smooth transition around 10, and when you are much larger than 10, you have a Granular regime where the shear viscosity and normal viscosity scale linearly with the Stokes. Okay, so I can plot also the mu, which is the ratio between the shear stress and the pressure, and which is the ratio of the shear viscosity and the normal viscosity. And you can see that we have a Newtonian regime for a Stokes number, which is smaller than 10, but larger when it's larger than 10. There is this effective friction coefficient, which is decreasing with Stokes. And this is due to the fact that we have a slower transition to the Granular regime for the shear stress, much smaller from the shear stress than for the pressure. And what I want to show you, and which really was very surprising for us, is that we took the data from Bagnol. I told you that he had a set of experiment where he looked at the transition. So he used a different system than us, different spheres, different fluid. He had water and glycerin, everything different. But you see, we put his experiment here, this diamond here, which are, this is in blue, it's a glycerin, and in pink, it's water. And he observed the similar transition around Stokes of 10. And it's really located in between our data, which is very surprising, but very encouraging at the same time. Okay, so basically, if we have a crossover from viscous to inertial flow at a Stokes number of 10, which is independent of phi. Here, I have collected all the data and normalized on the Rheology inset here. It's normalized by the value here on the plateau, which is for the Stokes, which is very small. And you can see that we have this transition, and it's around 10, and it's qualitative agreement with numerical simulation of friction and sphere, although they found a transition for a smaller Stokes number, okay, which is about 1, 2 here in the experiment. We found it for 10. Now, let's look at the rheological data collected in pressure imposed rheometry. Okay, and and really the idea is to try to have a unification using stress additivity, as was done in the numerical simulation that I presented before. And this is what we did here. We plotted mu and phi normalized by mu c and phi c. Here we have the same type of system plus a dry and water immersed condition, which two additional experiments with dry particle and with water immersed particle. And you can see that we can collapse very nicely phi when it's plotted versus j plus alpha I square, with alpha being the inverse of the Stokes number, the Stokes at the transition. The Stokes number at the transition is 10. And here it's so the alpha is 0.1. But we cannot collapse the data for mu. So what we did is we tried to find another alpha, which is here. And we have an alpha mu here, if we want to collapse the data, with a smaller alpha mu, which is characteristic of a larger Stokes, transitional Stokes, a transitional Stokes for this effective friction coefficient, which is around 100. And actually, yeah, we have two distinct scaling for the packing fraction and the stress anisotropy mu. And this is not captured by the numerical simulation that I mentioned before, because they have exactly the same alpha. But in the experiment, it's that we found, and it's really due to the fact that, as I mentioned before, the shear stress is transitioning much slower than the particle pressure. And so we have a transition, we take more time, and we have a second transition for mu. Okay. Now, you can attempt to find constitutive law, and from this pressure imposed rheology, I can plot phi and mu versus the additional stress scale, as I mentioned before. And you can see that I can find this exponent here, which is the exponent of for the phi and for mu, which is gamma phi and gamma mu, and they are identical. They can call them gamma, and it's 0.5. And actually, now this is the pressure imposed view. Now, if we want to move to the volume imposed view, you can normalize by the addition of stress scales, the shear stress and the pressure, and you get the divergence versus when you plot the data versus the distance, for instance, to the jamming here, and you have an exponent which is -1 divided by gamma, which is this exponent 2, -2. So you have the same divergence across the viscous and the inertial regime. And we can have some constitutive law that I have given here. So you can see that the pressure is really just diverging like that, like phi c minus phi with a coefficient which is here. And the shear stress is also diverging, but there is this mu, which depend on phi, and Stokes, which is the effective friction coefficient, which give you a divergent, which is a little bit slower. Okay, so this is what we important thing that we have for this transition. And now I'm going to move for the last minute across the jamming and viscous to inertial transition. Instead of having some rigid particle, I'm going to use a soft particle. And really, the idea is to look at the rheology of soft and smooth particle. And this particle, you have all sorts of soft system in industry or even in nature, but probably more in industry. And this some soft system, they are a weak elastic solid at rest and low stresses, but liquid above heel stress. And basically, it's because you have what we call elasto-hydrodynamic lubrication. And when you have two particles like that and you shear, this particle, there is lubrication between the two particles which can develop. And lubrication layer, this lubrication layer develop a very high pressure, lubrication pressure. And this is deforming the particle, and therefore the particle can flow, the system can flow. And this is describing the flow above the heel stress. So this has been studied for a very small particle, mostly colloid, and also in numerical simulation. And the idea here is to look at what's going on when you have large particles. And we did again, we use or pressure imposed rheometer. We run it in a pressure imposed condition or in volumetric condition with hydrogel. This hydrogel has very low friction between the particle, and we mixed this hydrogel with Yukon water and citric acid a little bit. Actually, we use citric acid because we can grow the hydrogel and the citric acid so they don't become too big. But basically, using a certain percentage of Yukon oil, we have different viscosity again. We can vary the viscosity. Unfortunately, it's changed a little bit the diameter of the particle and also the Young modulus. So the particle are smooth. They are a little bit, they have a, but you can see Young modulus is about varying from 127 to 232. It's a little bit small. Okay, and we do again this pressure imposed rheometry. And here I plot the effective friction coefficient and the volume fraction versus the addition of stress scale. And you can see that we have data. If you look at the data for the volume fraction, we have data across the jamming transition for different imposed pressure, because you impose different pressure and the particles are deforming. So you can reach volume fraction, but you cannot access, which are above the jamming transition, that you cannot access for odd sphere. And here we have plotted with exactly the same coefficient versus the J plus alpha I square, you can see here, and exactly the same coefficient alpha phi and alpha mu as in the previous experiment with the odd sphere. And of course, we have a better collapse for mu when it's plotted against the J plus alpha mu I square, like we had before. Now we can normalize everything by phi c, there's a different phi c here or different mu c. You can see that there's different phi c, and there is actually, you can, the big difference between the art sphere is that you will normalize your data because you have pressure dependent mu c and phi c, because your system, as we've seen here, there's different phi c which depend on the pressure, depending on the pressure. And this is, you can see that you can collapse your data very nicely. The dashed line is what you get for an odd sphere. And now the new thing that you have to take into account is this pressure dependent mu c and phi c. The nice thing is that you can renormalize everything with mu c and phi c with the value at jamming again, but this value are dependent on the pressure. And this is the model that we have chosen. We have different asymptotic behavior, of course, for the we can define this soft granular rheology where you have phi divided by phi c and mu divided by mu c, with again the addition of the stress scale. Of course, we have a different here exponent. You remember that before we have an exponent of 0.5, here it's 0.3 because our system is extremely low friction. So it's clearly what we have is that we are pretty close to friction in sphere, and there is some prediction from friction in the sphere, which with an exponent of 0.35, but in fact here we have 0.3. But the new thing, which is very important, is this phi c and mu c, and you see that there is a pressure dependence of phi c and mu c. We have normalized the pressure by the only thing that we can normalize with, which is the Young modulus here of the particle. And you can see that the phi c divided by phi c0 is plotted here. This is from the experiment. This is pressure, and you can see that it's increasing, and you can just model it by a power law here, which is something which is P divided by E with a power law with an exponent X. And we found an exponent of 0.67, which is close to the 2/3, which denote Hertzian contact. Basically, our system is smooth, and it's Hertzian contact that we have, and this is what it shows. For mu c, this is mu c, which is plotted here, and you can see that it's pretty flat, and it's pretty close to mu c 0 for zero pressure, and it's of about 0.11, meaning that your system is close to frictionless. It's very without any friction. So basically, what we have is a system where we have a new soft granular rheology, when you can again normalize everything by phi c and mu c, but with pressure dependent value of this phi c and mu c. Now we can normalize again. We can plot everything in terms of shear stress and pressure normalized by the addition of the stress scale like we did before. And we have some divergence again, but the divergence is not -2, it's minus about a little bit more than 3, because we have this particle, which are really a little bit soft and smooth. Okay. And it's what you can see here. We don't have it. We have a different divergence because we have some smooth particle. Now, the important thing now is that we can look at the critical rheology around the jamming transition, and we can collapse everything on two curves one above the jamming and one below, by scaling the shear stress and the pressure as parallel of the distance to jamming. You see what we have this shear stress and the pressure that we normalize by 1 minus phi divided by phi c0 with an exponent delta. And here we have also the shear rate, which are just the addition of the viscous and inertial before. And we have also power law of the distance to jamming, because we have 1 minus phi divided by phi c0 with a gamma here. Okay. And you can see that we can collapse everything with two curves. And it's really similar to the theoretical model and simulation of soft particle and rheological measurement of viscous soft colloid, which has been done before. But the difference here is that we are not only in the viscous regime, we are also across the transition and in the inertial regime. So we can expand that. And we can, the important thing is that this exponent delta and gamma that people have been seeking for a while in the in this paper that I mentioned here, we get them directly from the soft granular rheology, because delta are just 1 divided by x, okay? And gamma, which is here, it's 1 over x plus 1 over gamma. Gamma, what we deduce from the pressure imposed data. And now we can have this soft granular rheology, which describes the rheology of non-Brownian soft particle on both sides of the jamming transition. When phi is larger than the jamming volume fraction, you are on this branch here above this upper branch here and here for the shear stress and the pressure. And you have a generalized Urcher-Berkeley law with a here pressure here and a shear thinning exponent here. And the curve you see here are coming directly from the rheology, the soft granular rheology that we wrote before. Now, when phi, so you have this different branch, and you can see that when phi is very close to jamming, we have a power law with an exponent which is 0.3, which is here, okay, here. And you have also a lower branch where you have also, it's joining in the power law, but when you are far from jamming, here you are linear, because you are, the fact that the particles are soft is less important. Okay. So I'm going to the conclusion now, and I hope it was not too technical, but I wanted really to show you that you can unify granular and suspension flow, and you can use a volume imposed or pressure imposed rheology. And the pressure imposed rheology is very interesting if you want to look at the rheological property very close to the jamming transition. I've shown you that there is this transition from Newtonian to Wagnerian rheology that we have studied, and we have been able to unify these two regimes. There is a transition for Stokes number of 10, which is independent of the volume fraction. And you can scale everything using stress additivity. But there is a different transition from the shear stress and the particle pressure, which is embedded in the stress and isotropy mu. And mu It's actually it's a stress anisotropy, but it's really linked to the structure of the suspension, and really it could be that in our system there is a different behavior of the shear stress and the pressure, and it may be due to the inertial response of the system, and also the structure of the suspension. The last part I show you, it's about the soft granular rheology. And you can see that if you have soft particles, you can develop you can expand this granular rheology, which was made for the hard sphere, and you can expand them to a soft granular rheology, and we can capture the critical rheology across this jamming transition above and below the transition, and also across the different flow regime, which is the very new thing, is that we can be across the viscous and the inertial regime. Okay, thank you very much for listening to me.
Thank you, Elisabeth, for this insightful presentation on the rheology of dense suspensions. If you have questions, we invite the audience to ask comments or questions in the chat, or please feel free to unmute yourself and ask questions directly.
Can I ask a question?
Yes, please. Yes, please. Hi, Thomas.
So, okay, thank you for this very nice talk. So could it be that the difference in the Stokes number transition between tau and P is because tau is, as far as I understand, a mixture quantity, and P is a particle phase quantity? And
it's an interesting question. It is true. It's actually, if you think about mu, which is the ratio of the two, which is really what is the problem. Mu is really linked to the structure of the suspension. When you do numerical simulation, and it is clear that there may be some different structure which develop in the viscous regime and in inertial regime, and which make it. I don't know. I don't know exactly, but this is what I think.
I think one could test this with numerical simulations when one
exactly. This is what we're trying to do right now. We have been discussing with Bernard Wowinkel, whom you may know. I don't know. He's in Germany, in Dresden, and he is. They have this nice code. I think it's very similar to what you have, Aman. Huh?
Yeah, I know.
Yeah, I'm not an expert in numerical simulation, but you have to think that the numerical simulation which were done to model the transition, like done by Martin Trolson and other people, there was, or in the group of Farah and Rajai, they used DEM and they had lubrication, but they didn't have the full hydrodynamic interaction between the particles. So it could be that there's some, you have to take into account some hydrodynamic to account for the structure of the suspension.
So what kind of interaction did they not have? You said they didn't have the full
long-range hydrodynamic interaction, I think.
Okay. Okay, thank you.
I don't know, but I agree that it's really maybe linked. We don't know exactly. We were surprised when we got that from the experiment, but that means that we need to understand what's going on. Why the shear stress and the particle pressure are not transitioning exactly in the same way.
I mean, one thing to test could be just taking the particle shear stress in simulations and looking how that behaves.
Exactly, yeah.
Perhaps maybe I can ask another question while it's related to that. In the experiments, you consider these spherical particles, right? So when you consider polydispersity or shape of the particles and so on, do you think it will change the scaling, the rheology, or it's just only change the coefficients, or any insight?
Well, if you have spherical particle, if it's a little bit polydispersed, I don't think it's going to change much the divergence. Of course, if you have elongated particle, it will change the asymptotic behavior. You remember when we did, we look at fibers in the viscous regime, and the exponent was not -2. I mean, it was -1. So since when you are close to jamming, the critical behavior really depend on the network of contact. Depending on the shape, the shape of the particle will be important. Will be really a critical thing. So I think if you change the shape, it will change the critical behavior.
Okay.
Yeah.
Okay.
But just one thing about this critical behavior is that we try to unify things, but somehow I don't know if we're going to succeed, because the critical exponent are depending really on different things. The shape of the particle, the phi c and the mu c are depending on the contact, nature of the contact. So,
yeah, it's interesting thing to think about. Yeah. Also, when you think about in these scalings, you are relating local shear stress with a local pressure, right? When you have dynamic system like sediment transports, there are also time scales and length scales which might go into these relationships. It's an interesting work to look at more closely also in the context of sediment transport.
yeah.
I find it interesting. Yeah.
Yeah, this is something that we're doing with Pascal. We're trying to look at sediment transport, and we're going to try now to use this rheology in the sediment transport.
Okay. Okay.
The idea to look at, because before we look at, with Pascal, we look at what's going on in the viscous regime, but now we want to look at what's going on when your inertia is more important than when you are in the transitional regime in particular.
Can I ask a question?
Yes, please. Yes.
Hello. It was just a question, sort of trying to connect back to your first slide, where you were showing us a landslide, and you could see that the landslide was carrying very large rocks. And
okay, I'm going to try to go on my the first.
I was wondering if you can connect, I guess, all you have understood this rheological information about the capacity of this flow to carry such large loads, basically.
Okay. There is some, well, me, I'm not geophysicist, of course, but we have a lot of contact with geophysicists, and in particular, we're discussing with Anne Mangenet, that you may know, which is, she's working at the Institut Physique du Globe in Paris.
Okay. Yeah.
Which is actually part of a university, and they try to model this landslide, avalanche, and things like that. But this thing that they get this kind of landslide or debris flow, they can carry this huge boulder, is really interesting. It looks and sometimes they have modeled that like two types of fluid, like you have a mud, which is a kind of fluid with a heel stress. And then you have this larger particle which are flowing in it, that they can carry it. I know that people have done that.
Okay.
And, but we're trying to do a very more fundamental thing. But I think we have been discussing a lot with people in geophysics. And we organized 2 years ago a program at the Kavli Institute with Ekamebo and other people with two-phase flow with application to zero physics. And I think it's very important to discuss. We've been discussing also with Nie Ishihara, who is in Japan and who is the volcanologist, and they are very much interested also in the rheological study we're doing, because they can use them later on. Yes.
Mm-hmm.
I don't know if it's replying to your question.
Yeah, thank you. Well, I guess it's not an easy problem.
No.
Yeah, thank you.
Can I ask you one question? First of all, thank you for a very nice talk. I think I know individual works, the way you put together, it's fantastic, and bring this talk to Australia. So you mentioned earlier that it's the first time virtually visiting Australia. I'm hoping in the near future you could actually visit us in Australia. So
hopefully, yes. It's a long way, but
yeah. My question is because you mentioned about the transition of exponent because the particle size from spherical to fiber from 2 to 1. We're actually looking at the particle shaping a way, because if I'm really thinking about fiber on the shear, so they were after certain shear durations, so align well with the flow region. So is it actually because of the particle shape, or is it actually because of the fabric of this particular flow? So my question is regarding that aspect.
I think they may align, or at least they may have some part where they align. But I think it's really, well, if you think about jamming as or at least the exponent due to the network of contact, you understand that from sphere to fiber, that will change drastically, of course. And so we did an experiment with a very viscous thread, very dense system. It was published in Journal of Fluid Mechanics a while ago with Franco Tapia and there was my colleague Jason Butler and Olivier, of course. And we discovered that the exponent was -1. Of course, the volume fraction was depending, phi c, I mean, the maximum volume fraction was depending on the aspect ratio of the object. So unfortunately, in our system, we cannot see whether the particles are aligning or forming packets or forming clusters. It's well, difficult.
Yeah, but thanks for all this work, because I think the experiments actually I'm a modeler, right? So it's bring us so much topics that I think as a modeler, so what we can look at in the future.
Yeah.
I think there's no any more further questions. Perhaps I can ask one last question. Any perspective? Any because I come from turbulence background, so do you have any perspective on looking at this problem of rheology from when you have turbulence at the interface, for example, sediment transport? Can these models be extended as well to account for turbulence?
Turbulence, I don't know. Turbulence, I have no idea. It's much more difficult. What we try to do with Pascal is try to look at the sediment transport and look at the inertia and see whether like the addition of the stress scale is working. So this is something in progress, and we hope that we can tell you more soon. But things are going very slowly.
That's right. Yeah. So I think if there's no any further questions, maybe we can wrap up here. Thank you, Elisabeth, for finding the time and giving this talk. We appreciate it. And yeah.
Yeah.
Right.
I can stop
Mhm.
sharing.
Thank you.
Thanks for inviting me. It was nice meeting you all again. And
Mm.
Aman,
Our,
it was
our
nice
pleasure.
meeting you.
Our
Okay.
pleasure. Hope to see you in
Bye-bye.
Australia.
I hope so.